We're going to present today a macro-scale model on how actin and myosin work, activate the muscle contraction and whatnot. Arman already talked about muscle contraction and the differences between the cross-bridge model, which is what we are trying to show here. So we basically came up with a model that, takes advantage of some principles of mechanics, electricity, and magnetism. So, and what we did was to emulate the interaction between actin and myosin, and we wanted to make a model out of that. And here, what we wanted to do is to put the different phases of the process, and here we try to blow up a big image of a muscle and try to show what's happening inside. If you would use a super duper microscope, to zoom in into the nano scale and see what's going on. And the intention for this is to show elementary school kids, middle-aged school kids, how their muscles work during physical activity, and try to awaken the interest of these students into biology, into science, into the science of our bodies. So we're going to start with the model. We're going to start how this thing works, and Kent is going to start the animation. I'm going to walk you through it, right? So initially, what we're seeing now is the lights are off, as you can see, which means that the myosin is going to be attached is in the attached state. So at this point, you have the stroke. Once actin is attached to ATP is attached to myosin, the lights turn red, meaning that there's some detachment. There's the corresponding detachment of the myosin to the actin. Then you start moving more, and then you see the ATP hydrolysis, in which we see that there's some hydrolysis of ATP into ADP and inorganic phosphate. And then the cycle starts all over again. You form the cross-bridge state interaction, and then the cycle starts all over again. So here we can see how myosin interacts with actin and the movement happens. So here's the critical part in which we want to have the transfer between beats, and luckily it's happening. And that's basically, it's a pretty simple, straightforward model in which you can see how an actin beat, the magnetic interaction between the magnets in the myosin head can move the myosin, the actin filaments with different colors and whatnot, and that's pretty much it's a simple model, but effective. We believe it's an effective model, and we came up with a no, you can transfer. It's transferring. Don't worry about it. Don't worry about it. This is working. It's going to like the little train that there's a kid's story about that, and so basically that's what we have here. We've spent several days, long hours trying to come up with a good model, and finally we were able to make it. And this is how it works. Now I'm going to pass it on to Kent, and he was going to explain a little bit on how the model was built, the mechanical parts, electrical parts, the magnetic parts, and with help of a presentation, help of part of the presentation.
So most of the mechanical aspects are pretty well on display as far as the linkages and everything else. And you got a pretty good display of how the actin, which is represented by the magnetic cylindrical beads here, gets passed off between the magnetic components. We just have neodymium, very, very high strength magnetic rings on there. But there's actually a fair bit to the component which is hidden in the background that you can't see, and that's primarily the electrical components. So for this, we had to come up with a nice circuit that would effectively light the switches and or light the LEDs in the manner that we wanted. So we used 3 bicolor LEDs, and with those, they rely on being able to apply a forward voltage and a reverse voltage. So for this circuit, which you can see here, we have 2 detect switches, which are attached to the backing of the board. And so when both switches are open, essentially it's just a forward circuit, and you have a forward voltage running through, and the LED lights red. For the off stage, when what we refer to as switch 1 is closed, it essentially kills the circuit, cuts off the current running through, and you just have a dead circuit there. When the second switch is closed, so you have switch 1 and switch 2 closed, you can effectively reverse the current through the circuit, and then the LED is light green. So that's kind of just the electrical side of things, but obviously we had to be able to time this out and have it running in a very timed, precise manner with the motion. So for this, we machined out a switch plate from a piece of nylon, and that's basically epoxied right onto the back of this pulley. We have the 2 detect switches lined up under here, and the detect switches basically have a little spring in them. So when the various portions of the switch plate come in contact, they'll activate the different switches as you go into rotation, and you know that the switches are going to light in the same manner every time. This is just kind of an interior view of what we got here. Breadboard and the main circuit components are kind of hidden away and blocked off from the rest of it, just to kind of keep the wires and circuitry away so you don't get random hands poking in and shocking themselves or whatever. And then just a basic rod supporting biomagnetic beads there. And then just looking from the back, we have a handle that we machined out, as well as the battery pack for easy access, and then the on-off switch. So it's fairly easy to operate and requires very little maintenance. If you just want to hand it off to somebody, let them take it out and give it a spin. So that's essentially most of the mechanical components there. If you have any questions or anything else, this would be a good time.